In this video, we'll be talking about the preparation of carboxylic acids, and this includes natural sources as well as synthetic methods. Thinking about natural sources, there are a lot of naturally occurring and biologically important carboxylic acids. This is the simplest carboxylic acid, formic acid, and this is produced by some ants. Acetic acid is better known as vinegar. Amino acids make up all of our proteins. This is lactic acid, which collects in our muscles after a really vigorous workout. This compound, where we have a benzoic acid with an OH next to it, this is called salicylic acid, which is a pain reliever, but it irritates the stomach. So putting an acetate group on this makes this acetylsalicylic acid, better known as aspirin. And down here we have a couple examples of fatty acids, which are long-chain carboxylic acids. They might be saturated or unsaturated, where there's at least one double bond. Fatty acids form triesters with glycerol, forming triacylglycerides. If all of the fatty acids are saturated, then the triacylglyceride tends to be a fat, so a solid, whereas if there's one or more unsaturations in the fatty acids that make up the triacylglycerides, this introduces a kink into the chain, which means that the molecules can't pack together as well. And so these triacylglycerides tend to be oils. This is a very small selection of some naturally occurring carboxylic acids. Carboxylic acids can be prepared by oxidation, and here we have a few examples. First of all, oxidation of alcohols. Primary alcohols are oxidized by chromic acid, which is usually prepared from potassium or sodium dichromate in the presence of sulfuric acid. And this will give us, in this case, propanoic acid, also known as propionic acid. In addition to chromic acid, there are other methods that will oxidize primary alcohols to carboxylic acids, but do keep in mind there are some methods such as PCC oxidation or Des-Martin periodinane, Swern oxidation that will convert primary alcohols to the aldehyde. And so it's different conditions to get the carboxylic acid. Aldehydes themselves can be oxidized, again, using sodium or potassium dichromate, sulfuric acid, and in this case, it will give us the same propanoic acid. And a third type of oxidation is the oxidation of an aromatic side chain. So for example, if we take toluene and we treat it with sodium or potassium dichromate, sulfuric acid, then this will be converted to benzoic acid. For the oxidation of an aromatic side chain, the benzylic position must have at least one hydrogen, and whether you have a single carbon or a huge chain of carbons, what you'll end up with is a benzoic acid. So you must have at least one hydrogen at the benzylic position, and the carboxylic acid ends up at the benzylic position. There are a few ways that carboxylic acids can be prepared by oxidative cleavage. If you have an alkene in which the alkene carbon has at least one hydrogen, then treatment with concentrated potassium permanganate, this is going to give a carboxylic acid. For this particular example, the alkene is cleaved here. This carbon becomes a carboxylic acid carbon, and this carbon becomes this carboxylic acid carbon. Keep in mind there are other ways to carry out the oxidative cleavage of alkenes. If you use ozonolysis, this starting material would give two aldehydes. So ozonolysis of alkenes doesn't give a carboxylic acid, only potassium permanganate. But furthermore, if our alkene had R groups rather than at least one hydrogen, then this would give a ketone rather than a carboxylic acid. Alkynes can also undergo oxidative cleavage, and in this case, ozonolysis can convert the alkyne carbons into carboxylic acid carbons. So an alkyne is cleaved so that this carbon becomes this carboxylic acid carbon, and this alkyne carbon becomes this carboxylic acid carbon. Another way to prepare carboxylic acids is by the carboxylation of Grignard reagents. We've seen that Grignard reagents can act as very strong nucleophiles and add to aldehydes or ketones or esters. If a Grignard reagent is combined with carbon dioxide, this carbon is electrophilic, and so the Grignard can add to this carbon, pushing, let's say it's these electrons that move over onto this oxygen. That gives us an intermediate that looks like this. And then on aqueous acid workup, we will be able to isolate the carboxylic acid. As another example, we could start with bromobenzene, and treatment with magnesium leads to the formation of the Grignard reagent, and then treatment with carbon dioxide. This will attack here, pushing these electrons onto one of the oxygens, giving us this intermediate. And then with aqueous acid workup, the carboxylate will grab off a proton from the H3O+, leading to the isolation of this carboxylic acid. Notice with both of these examples, if you compare our Grignard reagent to our carboxylic acid product, we have one additional carbon. Carboxylic acids can also be prepared by the hydrolysis of nitriles. So if we have a nitrile such as this, for example, it can be hydrolyzed either under acidic conditions or under basic conditions, giving us a carboxylic acid plus ammonium byproduct. We're going to talk about the mechanism in a later chapter, or if you're really curious, you can look it up. Next, let's think about both the preparation and then the hydrolysis of nitriles. So for example, we have seen SN2 reactions where an alkyl halide can be treated with cyanide. Cyanide is our nucleophile. It can add to this carbon, pushing away bromine as a leaving group, giving us this product. In a second step, this can be treated with water and acid or base, and that will give us this carboxylic acid. Notice if we think about our alkyl halide starting material compared to our carboxylic acid final product, we have one additional carbon. Another reaction to prepare nitriles involves nucleophilic addition to an aldehyde. So in this case, cyanide can add to the carbonyl carbon, pushing these electrons up onto the oxygen, giving us as an intermediate this, and then H3O plus, in this case it refers to very mild acid, just enough to protonate this O minus, which gives us the cyanohydrin. And then Hydrolysis under acidic or basic conditions will give us a compound that looks like this. So if we focus on our carboxylic acid and then we start naming the carbons adjacent as alpha, beta, gamma, what we have here is an alpha hydroxy carboxylic acid. Let's consider different methods of the preparation of carboxylic acids. If we're starting with ethanol and our goal is to make acetic acid, let's count our carbons. We're starting out with 2 carbons in our starting material, 2 carbons in our product, so all we need to do here is carry out an oxidation. So if we treat this with potassium dichromate, sulfuric acid, and water, then this primary alcohol will be converted to a carboxylic acid. In our next example, we're going from, in this case, ethanol to propanoic acid. So we're starting out with 2 carbons, but our target has 3 carbons. So just carrying out an oxidation isn't going to work. Well, let's convert this to an alkyl halide. So we can treat this with HBr or PBr3, and that will give us ethyl bromide. Now, one possibility is we can treat this with magnesium to form the Grignard reagent. Now, this can be treated with carbon dioxide, followed by aqueous acid workup, and this will give us propanoic acid. Alternatively, our alkyl halide could be treated with cyanide to do SN2 substitution, which would give us this nitrile, which could then be hydrolyzed under acidic or basic conditions to give this carboxylic acid. In this particular example, either the Grignard approach or the nitrile approach would work. There might be some cases where you can't carry out SN2 substitution, then you would have to go the Grignard approach. Or you might have a substrate with a functional group that's not compatible with Grignard, then you would want to do the nitrile approach. But there are other examples like this one where on paper, either one is just fine. If we look at our last example, we are going from a 2-carbon alcohol to a 3-carbon alpha hydroxy acid. So we know that we need to use an aldehyde, and we should think about this part as coming from the aldehyde. So starting with our alcohol, we need to carry out an oxidation. We can't do the same thing that we did up here because that would give us the carboxylic acid. Instead, we can use PCC or Des-Martin or Swern oxidation, and this will give us this aldehyde. Next, we can treat this with cyanide, followed by dilute acid, which will give us the cyanohydrin, and then stronger acid to carry out the hydrolysis, will give us the alpha hydroxy acid. There are several different ways to make carboxylic acids. Here we've considered just a few of them.